Welcome back everyone. In this lecture we will continue to prove other Seilos theorems. So let us recall what we proved so far. So we proved the first Seilos theorem, which actually guarantees that Silo P subgroups exist. So let us start with G being a group, and then let's say G has cardinality of G is exactly some P power K times M, where M and P are relatively prime. Okay, this is the data given. So where P is a prime number. Okay, so you fix a prime number P, and then you write cardinality of G equal to P power K times M, where M and P are relatively prime. That means P power K is the largest power of P that actually divides this cardinality of G. So then what we proved, so this is the statement of Seilo's first theorem. So which says Silo P subgroup actually exists. That means there exists H subgroup of G, okay, such that order of H equal to P power K. So any subgroup of order P power K is called Silo P subgroup. Okay, so H is called a Silo P subgroup. So note that we can actually denote this capital S I L O of P to be set of all Silo P subgroups. Okay, the set of all Silo P subgroups of G. Okay, then we just simply proved this is actually non-empty set. So since G is a finite group, there are only finite many subgroups of G. So this Silo P G, that is actually a finite set. Okay, so we are interested in understanding, okay, so what is the cardinality of this set, and any other relationship are there between the elements of this set. Okay, so that is what guaranteed in the second and third Seilos theorems. Okay, the second Seilos theorem says there are some relationship between any two given Silo groups. So let me state the second theorem. Seilos second theorem. So which assess something. So if we take two Silo P subgroups, so then we can prove that they are conjugate inside the group G. That means there exists G in G such that H is conjugate to this K. So G H G inverse equal to K. So they are conjugate under this inner automorphism defined by this G. So now this says that up to this conjugacy relation, you can actually define the action of this G on this set of all Silo P subgroups. Okay, so then this second theorem can be rephrased as the group G acts transitively on the set of all Silo P subgroups. Okay, so in other words, you have the action. So G acts on the Silo P subgroups via conjugation. Okay, and this action is transitive. So this action is transitive. So that is the meaning of the second statement. So note that if you take any H which has order P power K, then if you take any conjugate of that, that will have order P power K. So that way you always have this action of G on the set of all Silo P subgroups. So that is not a problem. The important part of the statement is this action is transitive action. Okay, so let's try to understand this result. Okay, so if we think about it, okay, so we want to actually prove that okay, given two silo p subgroups, they are conjugate. Okay, so how do we proceed this? So we can fix these subgroups. Okay, so here is the proof. So you can fix these subgroups of G such that both of them are actually silo p subgroups. That means both of them have cardinality p power k. So then what you can do, you can make k act on this G modulo H via conjugation. Okay. So this is indeed okay. So this is not via conjugation, this is just by multiplication. So you can take the left multiplication action of G on G mod H, then you can restrict that action to K. So that is the action that we are talking about. So K acts on G mod H via this small k dot AH is given by KAH. Okay, so this is the action that we are talking about. But note that K is actually silo P subgroup. In particularly, the order is P power K. So in particular, it is a P group. So K is a P group. Okay, that means it has order which is power of prime. So if you take X to be this G mod H, then using the result that we proved for the action of P groups, we can immediately have. So if you write that class equation or that orbit decomposition of this X, okay, then we saw that the cardinality of X is going to be congruent to cardinality of X power K, because K is the group that is acting, modulo the prime P. So this is actually something we have already proved for P group. If a P group acts on some set capital X, then the cardinality of X is congruent to the cardinality of the fixed points of that X under the group action modulo the prime P. Okay. So that is what we have already. So now note that what will be the cardinality of X in this case? The cardinality of X is nothing but the cardinality of G modulo H. The cardinality of G modulo H, if you just work it out, it is just cardinality of G divided by cardinality of H, which is exactly equal to M. Because cardinality of G is P power K M divided by P power K is going to be M. But M is not divisible by P. So note that. So the M and P, they are relatively prime. That means what? That means the cardinality of X power K will be never 0 modulo P. Okay? That implies cardinality of X power K is at least 1. That's all we need. Okay? So this is guaranteed by telling that P doesn't divide the cardinality of X, and cardinality of X is congruent to cardinality of X power K. So that immediately implies at least cardinality of X power K is non-zero. Okay. So that means what? That means there exist some coset AH inside this X power K. So if you translate this, okay, this means this K acts trivially on this coset for all K in capital K. Okay. So let's rewrite this. So you can rewrite this as follows: A inverse K A H equal to H for all K in capital K. So you have this fixed A, okay, for which you can see that A inverse K A H is H for all K in K. But H is a subgroup. So that means what? That means this implies A inverse K A is an element of H for all K in capital K. So what is the meaning of this? This means if you take the conjugate of capital K under this A, so then this is going to be subset of H. So that's all it means. Okay, the conjugate of this capital K under this A inverse is going to be subset of H. But note that the cardinality of H is P power K and the cardinality of K is P power K. So in particularly the conjugate of K, that is also has cardinality P power K. So since it is a subset of H which has cardinality exactly cardinality of H, that forces that it is exactly equal to H. Okay, so H is equal to A inverse K A. But that means what? K is equal to A H A inverse. If we go back, we started with two arbitrary Silo P subgroups. We made one group to act on these cosets of another group and we got the fixed point, and that tells us that so these two groups must be actually conjugate to each other. So this proves all Silo P subgroups are conjugate. Okay. So let us try to understand this more closely. So if you take the Silo P subgroups, the set, okay. So then we can easily see that if I make this G act on this, okay. So you can make G acts on this thing, okay, via this conjugation. So G dot some group is nothing but GH G inverse, okay. This is an action. So that now because any two Silo groups are subgroups are conjugate, so this says that this action is actually transitive action. So this action is indeed transitive action. But we know something about the transitive action. The transitive action is isomorphic to the following action. For example, you can fix some particular element of that set, okay. If you fix some H inside, if you fix some X inside this Silo of P G, then if you look at the fixed points of this, okay. So what it will be, or you can actually look at this subgroup of G that fixes H, okay. So let us look at this subgroup of the or the stabilizer of H, okay, inside G. So this I am treating as it as element. So your set is this, okay, this is your set and this is element, and I am looking at the stabilizer of that element in G, okay. So if you look at it, what it is those G in G such that G dot H should be H. That means GH G inverse equal to H. But what it is nothing but the normalizer of H in G, okay. So then we have already shown that, okay, this G modulo GH has 1-to-1 correspondence between. There is a bijective correspondence. Not only bijective correspondence, it is actually G sets isomorphism. So G naturally acts on the left side on G modulo GH, okay. So you have this G sets isomorphism between this G mod GH and this Silo set Silo P subgroups. So that means the cardinality of this Silo P subgroups is exactly the cardinality of G modulo the cardinality of GH, which is exactly the cardinality of G divided by the cardinality of the normalizer, okay. So what is our intake from this? So this is index of some subgroup of G, okay. But any index of the group subgroup also divides the cardinality of the original group, okay. So since cardinality of G equal to cardinality of G divided by the cardinality of Ng of H times the cardinality of Ng of H. So, we can conclude that the cardinality of the silo P subgroups divides the cardinality of G. Okay, it is a very important conclusion. So, let us denote NP of G by this cardinality. Okay. So, right now already we have some understanding of this number. So, this number actually divides the cardinality of G, and not only that, this number is exactly equal to the index of the normalizer of some silo P subgroup of G. Okay. So, you can fix any silo P subgroup, then you look at the normalizer of that and then take the index of that normalizer inside G, that is going to be exactly equal to the cardinality of this silo P G. Okay. So, now let us look at this third theorem of silos. So, that actually tells what other properties this NP of G has. Okay. So, here is our third theorem. So, let me write it down. So, this asserts that the number of, okay, this is exactly the number of distinct silo P subgroups of G. So, this number NP of G is exactly congruent to 1 modulo P. Okay. So, that is what it says. So, when you take this number NP of G congruent to 1, it is exactly congruent to 1 modulo P. So, how do we actually prove this? So, let us see. So, note that already we know that NP of G divides the cardinality of G, which is exactly P power k times M. And using this third theorem, okay, this is the statement of third theorem, you can easily see that, okay, as a corollary, P does not divide NP of G. So, that means they are relatively prime. NP of G and P are relatively prime. Okay. If this is actually relatively prime, so then you can see that so this has to actually divide only. Okay. So, if you take if you take the prime factorization of this NP of G, so then the any prime P power, okay, should not appear in this NP of G. So, what we can conclude from this, we can conclude that if we take prime factorization of NP of G, so then power of, okay, this particular prime P, okay, cannot appear in that NP of G. Okay. So, because NP of G does not have any particular P does not divide NP of G. So, that means in case if you are actually factorizing, okay, P power k M equal to NP of G times some D, okay, then what you can see? You can see that there is a close relationship between this NP of G and M, namely this NP of G must divide M. Okay. So, this NP of G must divide M. So, this is just you can write down the prime factorization and then look at it. Okay. So if you take the prime factorization of m, you can see that, so except this particular prime p power k, all other prime factorization of this cardinality of G must appear in m. Okay. So let's write it. So let's say cardinality of G equal to some p1 power alpha 1, p2 power alpha 2, etc., pr power alpha r, where p1 let's say p, okay, and alpha 1 let's say k. So that means the cardinality of G equal to this p1 power alpha 1 times m. So m will be exactly p2 power alpha 2, etc., pr power alpha r. So now you have written this exactly equal to np of G times d. Okay, and note that no prime factorization of okay, so this p1 doesn't appear in the prime factorization of this npg. So p1 doesn't appear in the prime factorization of npg. So that means, so whatever primes that are appearing in npg, they have to come from this. Okay, and all the exponents are here for these primes. So these exponents, if pi some ri divides this np of G, then this ri has to be less than or equal to alpha I greater than or equal to 2. Okay, so that tells you that this np of G must divide m. And not only this np of G must be congruent to 1 modulo p, that is also there. So let's see how one can prove this. Okay, now again what we do, we fix one silo p subgroup, fix H to be one silo p subgroup of G, and then make H2 act on this set silo p G, again via conjugation. Okay, so we just take this H and then okay, make it act on this set silo p G. So this is the set now and this is the group now. So if you are not comfortable which one is set, which one is group, you always mention it and then you keep track of all those things. Okay. So now again, what is the cardinality of H? Cardinality of H is p power k. In particular, it is a p group. So that means if you call this is capital Y, then the cardinality of Y is congruent to cardinality of Y power H modulo p, again from our previous result. Okay. So that means this cardinality of this Y power H, okay, so that is going to be congruent to the cardinality of Y. So in case if we prove that this cardinality of Y power H is 1, so then we are done. Okay, because what is the cardinality of Y? So the cardinality of Y is the cardinality of this silo p G, so which is exactly npg. Okay. So now we have npg congruent to the cardinality of Y power H modulo p. So let's look at this Y power H. So what is Y power H? This is going to be those subgroups, silo p subgroups k in silo p G such that it is fixed by the action of H. That means if I take G k G inverse, that is going to be equal to k for all G in H. Okay. So that is your Y power H. So note that already H is there inside this Y power H. So it is actually non-empty, because this equation is satisfied by H. G H G inverse is going to be H for all G in H, because H is a subgroup. Okay, so this is already there. So now what we do, we take another K from this YH and see what happens. If you take another K, then what will happen? Then this satisfy GK G inverse equal to K for all G in H. So that means what? That means if you look at the normalizer of this K, that contains H. So that is the meaning of this. So these two are equivalent. Okay, the normalizer of K contains H. So that means if I compute this HK, you can see that this is going to be union GK G in H, but here you can see that GK is same as KG. So this is union KG G in H. So that is exactly equal to KH. So this just simply says HK is equal to KH. This is something we have already seen. I am just rewriting. So now using our criterion for when the HK being subgroup, you can easily see that in this case HK becomes subgroup. So HK is indeed subgroup of G. But what kind of subgroup is it? Okay, let's look at the order of this HK. The order of HK, we already know that it is going to be order of H times order of K divided by order of H intersection K. But what is order of H? Order of H is P power K and order of K is P power K. So then that is going to give us P power 2K divided by order of H intersection K. But this is going to be a subgroup. Okay, this order of HK must divide P power Km, because HK is a subgroup of G, that imply the order of HK should divide order of G. What it is? It is P power K times M, and M and P are relatively prime. So it says that P power K is the largest power of that P prime P, such that P power K divides R of G. So that means if you take this particular thing, okay, because H and K both are P groups, both having cardinality P power K, and H intersection K is a subgroup of H as well as K. So it has to be some, the cardinality of H intersection K also should be some power of the prime, okay, prime P. So then if you put it together, you can see that the H intersection K, if you write this as P power some alpha let us say greater than or equal to 0, okay, we do not know what it is, then you can see that P power 2K minus alpha divides the cardinality of G, which is P power K times M. But K is the largest power, okay, that means this 2 power K minus alpha should be less than or equal to K. There is no other option. So that will imply that K is less than or equal to alpha. Okay, but alpha is natural number, so it is actually it's positive number, non-negative number. So but we are saying that it is at least K, but H intersection K is a subgroup of H, that forces that it is at most K. So that means we indeed proved K equal to alpha. Okay, but when this K can be alpha, H intersection K, if it is P power K, that means H intersection K is exactly H as well as K. So this is the only time it can happen. But that means what? That means we have proved that if you take any K in Y power H, then that K must be H. Okay, that means the cardinality of Y power H, okay, this implies the cardinality of Y power H is 1. Okay. So now this proves that this NPG is congruent to 1 modulo prime P. Okay. So this actually completes the proof. Okay, so there are some important things to note. If you denote NPG by the cardinality of the number of the cardinality of silo P G, which is number of silo P subgroups of G, then we have immediately NP of G divides this cardinality of G divided by the P power K, and NP of G is congruent to 1 modulo P. So these two things are there. So this actually puts lots of restriction on NP of G. Okay, in many small orders, we will be able to determine explicitly what it is, what possibilities that can have. So that will actually going to tell lot about the group. Okay, so in my next lecture, I will actually explain that with more examples. Okay, so that means we can have many interesting applications of Sylow's theorem, because Sylow's theorem very rigidly says lots of constraints are there even for the Sylow P subgroups. Not only the existential, it also says Sylow P subgroups, okay, they are not something random. They have to have very specific properties. Okay, I will stop here. We will continue in the next class with some applications of Sylow theorems. Okay, thank you.